Hello everyone. The topic of our today's class is Wireless LAN or Wireless Ethernet or the IEEE 802.11. Before we go to further details, let's just see a brief introduction of the IEEE project. In 1985, the Computer Society of the IEEE started a project called the Project 802 to set standards to enable intercommunication among equipment from a variety of manufacturers. The relationship of the IEEE 802 standard to the TCP/IP protocol suite is shown here in this figure. And we can see that the IEEE 802 standard has subdivided the data link layer into two layers. These are the first one is the logical link control layer, that is LLC, and the media access control layer, that is the MAC. And this IEEE 802 project has defined the specifications for a wireless LAN and call it the IEEE 802.11. And this covers the physical and data link layers of the TCP/IP model. And this type of network is also sometimes called the wireless Ethernet. And the wireless LAN is also considered to be one of the fastest growing technologies in today's time. And this type of network can be found in college campuses, office buildings, etc. Coming to the architecture of the wireless LAN, the IEEE 802.11 defines two kinds of services, that is the basic service set BSS and the extended service set ESS. And the basic service set BSS is further subdivided into two. The first one being the ad hoc basic service set and the infrastructure basic service set. This is the example of an ad hoc basic service set and an infrastructure basic service set. Here in the first picture, that is the ad hoc basic service set, we can see that there are no access points used, while in the infrastructure BSS, there is the use of the access point EP. Access point is nothing but a device that creates a wireless LAN. So in the first picture, that is the BSS without an access point. Is a standalone network. And in this type of ad hoc BSS, data cannot be sent to other BSS. That's why this is called an ad hoc architecture. And here, in this kind of architecture, the stations can form a network without the need of an access point, and they can also locate one another and agree to be a part of one basic service set. And however, the basic service sets using the access points are referred to as the infrastructure basic service set. One example of an ad hoc BSS or ad hoc architecture will be transferring of files from one computer to another through cable without using internet. And an example of an infrastructure basic service set would be the use of mobile phones. Coming to the next type, that is the extended service set. This is an example of an extended service set. This kind of architecture is made of two or more BSS In this particular example, we can see that there are three basic service sets and with APs, that is the access points. Here, the basic service sets have the access points. So, each of these basic service set is an infrastructure BSS, but not an ad hoc BSS. So here the basic service sets are seen to be connected through a distribution system, this one. And this distribution system can be either a wired or a wireless network. And this distribution system will connect the access points in the basic service set. When these BSS are connected, the stations within reach of one another, they can communicate without the use of an AP. However, communication between a station in a BSS and the outside BSS occurs via AP. This means that when there is a connection between one BSS, let's take this BSS for example, then a communication between one end system to the other within one BSS may not require the use of the access point. However, when communication takes place from one BSS to other BSS, then the use of access point is required. And the IEEE 802.11 also defines three types of stations based on their mobility in a wireless LAN. Those are no transition. Next one is BSS transition mobility and ESS transition mobility. A station with no transition mobility is either stationary, that is not moving, or it moves only inside one BSS. The second one, BSS transition mobility. Here, movement can be from one BSS to another, but the movement is confined inside one ESS. That is, inside one extended service set. And a station with ESS transition mobility is the one where movement from one ESS to another is possible. Coming to the MSC sublayer of wireless Ethernet, the IEEE 802.11 or the wireless LAN defines two MSC sublayers. Number one is the distributed coordination function or the DCF, and the other one is point coordination function or the PCF. First, coming to distributed coordination function, this is one of the two protocols defined by IEEE at the MSC sublayer, and the DCF uses the CSMA-CA as the access method. That is, a carrier sends multiple access with collision avoidance. Let's just see the difference between CSMA-CD and CSMA-CA. The CSMA-CD is mostly used in wired networks, whereas the CSMA-CA is used in the wireless networks. And another difference is that this CSMA-CD takes effect after collision. That means they can detect the collision, while the CSMA-CA takes effect before the collision. That means here the mechanism doesn't have collision detection, but instead it has a collision avoidance mechanism. Let's see how exchange of data and control frames takes place in the DCF of the MSC sublayer. Here in this figure, before sending a frame, the source station, here the source station is A. The source station senses the medium by checking the energy level at the carrier frequency. And the channel uses a persistence strategy with backoff until the channel is idle. And after the station is found to be idle, the station waits for a period of time called distributed interframe space, that is DIFS here. Then the station sends a control frame called the request to send RTS. And after receiving the RTS and waiting a period of a time called sort interframe space, or the SIFS, then the destination station will send a control frame called the CTS, or the clear to send, to the source station. And this control frame indicates that the destination station is ready to receive data. And next, the source station will send data after waiting an amount of time equal to SIFS again. And the destination station, after waiting an amount of time again equal to SIFS, will send an acknowledgement to show that the frame has been received. Acknowledgement here is needed in this protocol because the station does not have any means to check for the successful arrival of its data at the destination. This lack of collision in CSMACD is a kind of indication to the source that the data has arrived. And in order to make sure how the collision avoidance aspect of this protocol is accomplished, the key feature used in this is a feature called the NAV, or the network allocation vector. Let's explain what an NAV is. When a station sends an RTS frame, this RTS frame will include the duration of time that it needs to occupy the channel. And the stations that are affected by this transmission will create a timer called the NAV that shows how much time must pass before these stations are allowed to check the channel for idleness. And each time a station accesses the system and sends an RTS frame, other stations will start their NAV. In other words, each station, before sending the physical medium to see if it is idle, first they will check their NAV to see if the NAV time has expired. And sometimes collision can also take place. So let's see what happens when a collision takes place. If there is a collision during the time when RTS and CTS control frames are in transition, that means this period is called a handshaking period. So when two or more stations try to send RTS frames at the same time, a collision might happen. So when such case takes place, then the sender assumes that there is a collision if it has not received the CTS frame from the receiver. The backoff strategy is employed here, and the sender will try to send the data again. And another problem is the hidden station problem. When this type of problem, one solution is that again the use of the handshake frames called the RTS and the CTS. Here it shows that the RTS message reaches the RTS message here from B. It shows that it reaches A but not C. However, because both B and C are within the range of A, this CTS message, which contains the duration of data transmission from B to A, will reach the station C. So the station C will know that some hidden station is using that channel, and therefore it will refrain from transmitting until that duration is over. So that is about the exchange of data and control frames. Coming to the PCF, that is point coordination function. The point coordination function PCF. This is an optional access method that can be implemented in the infrastructure network and not in the ad hoc network. And this PCF is implemented on top of the DCF and is used mostly for time-sensitive transmission. This is an example of PCF. And the PCF, or the point coordination function, it has a centralized contention-free polling access method. Here, the access points will perform polling for the stations that are capable of being polled. And the stations are polled one after another, sending any data they have to the access points. So to give priority to the PCF over the DCF, another interframe space called the PIFS has been defined in this PCF. PIFS is nothing but the short form of PCF IFS, that is point coordination function interframe space. And this PIFS is shorter than the IFS. And this also means that at the same time, if a station wants to use only DCF, but an access point wants to use the PCF, the access point will have the priority because uh, PIFS is shorter than the DIFS. So due to this priority of PCF over DCF, the stations that only use PCF may not gain access to the medium. So in order to prevent this, a repetition interval has been designed to cover both the contention-free PCF and the contention-based DCF traffic. And this repetition interval, which is repeated continuously, starts with a control frame called the beacon frame. So when the stations hear the beacon frame, they will start their NAV for the duration of the contention-free period of the repetition interval. And the wireless network is usually a very noisy one. So what happened is that the frames are often corrupted. So a corrupt frame um, has to be retransmitted. When a frame gets corrupted, then it has to be transmitted the second time. So for this, the IEEE 802.11 protocol, it recommends fragmentation. Uh, Fragmentation is nothing but the division of a large frame into the smaller ones, because it is more efficient to resend a smaller frame than the large one. So the uh, IEEE 802 standard recommends a fragmentation. And the frame format for the MSC sublayer consists of 9 fields.